In today's lesson, we'll be looking at resolution of vectors, where we are going to focus on the component form of vectors. And if you are not subscribed to this channel, kindly subscribe and hit on the notification bell so that when a new video is being published, you are going to be the very first person to be notified. Now let's start. So we said that in the representation of vectors, there are 4 ways. One, we have the diagram or graphical form, and it has been illustrated just like you can see here. We also have the component form illustrated by the vector OA, which is equal to xy, the Cartesian form, the vector OA, which is equal to xi plus yg, and the last one, that is the magnitude bearing form, that is the vector OA, which is equal to the magnitude of the vector OA and the direction or bearing of the vector OA. So this is what we talked about in the representation of vectors. Now this video is going to focus on how we can convert a given vector in magnitude bearing form to its component form. So this is what today's video is going to be about. Now let's stay tuned and move along. How to change a vector from magnitude bearing form to component form. Now this is what we are saying. If we have a vector in magnitude bearing form as r as its magnitude and alpha as the bearing, then we want to change this to component form. Now this is what you have to note. So first, you have to represent this magnitude to bearing form of the vector in the Cartesian plane and we proceed from there, which means we are going to draw our Cartesian plane here. Now let's assume that this vector is in the first quadrant in the Cartesian plane, which means our vector is going to be at this side. Now we are saying that this is the vector and has a magnitude of r, nicely written as this. Now we are saying that the bearing of this vector starts from the positive y-axis in the clockwise direction to where the vector is. That is, the bearing starts from the positive y-axis in the clockwise direction to where the vector is. So here becomes the bearing of the vector. And we are saying that the angle the vector makes with the x-axis is represented by theta. So we can represent the angle the vector makes with the x-axis by theta. So this is what we have here. Now, in changing this given vector in the magnitude bearing form to component form, there are 2 ways, and we are going to elaborate them one after the other. Now let's move to method 1. So let's write here as method 1. Method 1. So method 1 is going to focus on the bearing of the vector. That is, we considering the bearing of the vector, the original angle given to you in the magnitude bearing form. So we write here by considering the bearing of the vector. So we are saying that the bearing is what we have here as alpha. So the bearing of the vector, that is the bearing of the vector in the magnitude bearing form. So this is what we have. Now, since we are considering that part, then it means that we come back to our diagram and we join from the positive y-axis to where the vector is. So we have something like this. So it means that our focus now is on where the alpha is, the alpha angle is. Now from here we can see that there is an angle of 90 degrees formed here. So what next? What you are going to do next is that you are going to apply the trig ratios in getting alpha and then that of the relevant parts. So here it means that we have here to be y and we have here to be x-axis. So we have the y-axis and x-axis. Knowing well that this side too is also our x-axis. Beautiful. So by considering the trig ratios, then we can start with cos. That's the cosine. So it means that the cos of alpha is equal to, that is the adjacent. So the adjacent part of this diagram we know to be y. So that is y on the hypotenuse we know to be r. So we have here as r, which means in finding for y, it means y is equal to r cos alpha. So this is 1 when we are considering the bearing of the vector. Now we also go to the next one, that is the cosine. Sorry, that is the sine. So it means that the sine of alpha, we are talking about the opposites out of hypotenuse. So we know the opposite side of this vector is x. So we write our x here, divided by, now the hypotenuse part we know to be r. So we have our r here. Now by making x the subject, we have s to be equal to r sine of alpha. So once we have this, then we said that in component form, the given vector is written as xy. But we know our x here to be r sine of alpha, and then we know our y to be r cos alpha. So this is one of the ways that we can change a given vector in the bearing magnitude form to component form. That is by considering the bearing of the vector. So that is method 1. Now let's look at method 2. So you write here as method 2. So method 2, we are saying that we are going to consider the angle the vector makes with the x-axis. So you write here by considering the angle, that is theta, the angle the vector makes with the x-axis, and that angle we know to be theta. So if you consider that, it means that we'd have to clean this part, the illustration here, and focus on theta as well. So which means we are going to close this side of the vector and the x-axis. So we have a right angled triangle here. If you consider that one too, you can also apply the trig ratio, and we are going to take into consideration cos and sine. So we take cos of theta will be equal to, so the adjacent part, we know this side to be y. So the adjacent part of this is going to be x. And then the hypotenuse part we know to be r. So it means our s is equal to r cos of theta. And then when we consider the sine of it too, it means we're going to have sine of theta, which is equal to, now the opposite we know to be y, and then the hypotenuse we know to be r. So here it means that our r is equal to r sine theta. So in changing the given vector A to component form, we are saying that it should be x, y, which is equal to, now we know our x to be r cos theta. We also know our y to be r sine theta. So this is method 2 of changing a given vector from magnitude bearing form to component form. Now, this is what you have to consider when using method 2. Method 2, you are saying that you have to consider the quadrant in which the vector lies. And with this vector, we can see that it lies in the first quadrant. So according to the trigonometric quadrant, the first quadrant, all the trig ratios are positive. That is, the sine, cosine, and tangent, they are all positive. So it means all is positive. When you go to the second quadrant, according to the trig quadrant, we can see that it is only sine that is positive. So if I write s, it means sine. It is only sine that is positive. The third quadrant, you can see that it is only tan, or the tangent, that is positive. And then the last quadrant, it is only cosine that is positive. Apart from that, the rest are all negative. So since this vector happens to fall in the first quadrant, it means we are not going to negate the sign of either cos or sine. But if it happened to fall in any of the quadrants where sine or cos requires to be negative, then we have to negate it. Now let's assume that this vector happened to fall in this quadrant where we are saying it is only tan that is positive. So if the vector happens to fall in this quadrant, then it means that we'd have to negate sine and cos. So we'd have to come back here and put a negative sign here and put a negative sign here. But because with the quadrant you are dealing with, they are all positive, we just leave it as such. So that is one thing we have to note when working with method 2. But apart from that, when working with method 1, we just use the bearing or the angle given to you without negating anything or without taking into consideration any quadrant. But for method 2, you have to consider the quadrant in which the vector lies. Now, this is the two approaches in solving a question related to bearing magnitude when changing to the component form. Now, let's take practical examples on situations like this. So we have example 1 here, and it says that write the following vectors in their component form. Actually, there are a number of vectors here. That's a number of questions. So this is the first one. Now I want to write this vector in component form. So like we did earlier on, we have to represent this vector in the Cartesian plane, which means we draw it as that. And first, we have to focus on the angle. The angle will determine the type of quadrant the vector would lie. Since from here to here is 90, it means that the vector is going to lie in this quadrant. That's the first one. But if it happens to be 80 to 70 or more, then we can see that respectively is going to lie in their quadrant as well. It means that this vector lies this side of the Cartesian plane. And we are saying that the bearing will start from the positive y-axis to where the vector is in the clockwise direction, which means our bearing alpha, but then alpha now is 60, so it means that our 60 now is going to be this side. That is the direction of the vector, the bearing of the vector. Now, the angle the vector makes with the x-axis is definitely going to be this side. But how do we get it? We can get it by subtracting 60 from 90, because you know that the sum of angles in this quadrant is 90. So it means that you are going to have the angle mixed with the x-axis, that's the vector mixed with the x-axis, its angle is going to be 30 degrees. So it means that their sum is now 90 degrees. So we have this one. So in changing this vector to component form, then we have to consider two methods. So any of them works. So we are going to look at the respective two methods. Now let's move to method 1. So method 1, that is when we are going to consider the bearing of the vector given to you. That's the direction of the vector given to you. That is 60. And that formula we said is giving us, so we have V is giving us R sine come first. So it means sine of alpha, and then you have R cos of alpha, which means that our vector V is now equal to the R we know from the question is 6. That's the magnitude of the vector, 6 newtons. So we write here as 6. That is 6. And then we know that the bearing is what we have here. The alpha is the original angle given to us. That is 60. So you come and write as 60 here. That is sine of 60. And we repeat this one to 6 cos of 60. And our component form for the vector now becomes, so 6 sine 60 gives us 3 root 3. So 3 root 3. And 6 cos 60 gives us 3. So this is one of the ways that we can change the given vector to component form. Now we can also consider method 2. Method 2, when we are going to consider the angle the vector makes with the x-axis. And that one too, we said the vector V is given by R. But with this R, we are going to consider cos first. That is R cos of theta, and now we have R sine of theta. So we do that by considering the quadrants in which the vector lies. But in this vector, you can see that it lies in the first quadrant. In the first quadrant, all of the trig ratios here are positive. So we forget about that one, or don't pay much attention to that, which means V now is equal to, we know our R to be 6, and cos comes first. So cos of, now our theta is known to be 30, so we write our 30 here. And here we have 6 sine of 30. So in component form, the vector now is equal to 3 square root of 3 and have here as 3. That is 6 cos 30 giving us 3 root 3, and 6 times 30 gives us 3. So at the end, we are getting the same answers, and you can apply any of them in your solution. So you just have to stick to one and make sure you understand it and you apply. For method 2, we consider the quadrant seeing the vector lines. If you forget about this one, you are not going to get the right solution when using method 2. So that is that. Now let's take another example to solidify our understanding. So we want to write the vector 25 kilometers, 120 in magnitude bearing form to component form. So write our solution here. And to change this to component form, you have to consider first by drawing the Cartesian plane. So we can see that the bearing here is 120, and that will tell us the quadrant in which it lies. So you know the first quadrant from the positive y-axis here is 90. The next one here is 180, which means our vector is going to lie in this quadrant because 120 happens to fall from 91 up to 180 itself. So it means that we are going to have our vector lie in this quadrant. We are saying that from the positive y-axis to where the vector is in the clockwise direction gives us the bearing, that is 120. So you know from here up to that side is 120 degrees. And you want to find the angle the vector makes with the x-axis. The angle the vector makes with the x-axis, that is here, this side. So in doing so, we have to consider this logic. We are saying that the first quadrant from the positive y-axis to the x-axis here is 90, and we have added this side too. So if from here to here is 90, then what number can we add to 90 to get 120? And definitely is going to be 30. So it means 30 plus 90 gives us the whole of 120. That's from the positive y-axis to where the vector is. So if that idea is clear, then it means that the angle the vector makes with the x-axis here is going to be 30. So we write 30 degrees here, which means when we add the 90 to 30, we are going to get 120. So this is the representation of the vector in bearing magnitude form. So we want to change to component form by applying the two methods. Any of them works. So we are going to look at the two methods as well. So let's write it as method 1. So method 1, we are saying that we can consider the original angle given to us. That's the bearing of the angle. That is the vector E, which is equal to r sine of alpha, and the next one r cos of alpha. So this is what we are seeing. Alpha is now equal to, we know our r here. Now r was giving us 25. So that is 25 sine of, now alpha is 120. And then write the same thing as 25 cos of alpha, and alpha you know to be 120 degrees. So respectively, we can see that our vector E in component form is giving us, so 25 sine of 120 is giving us 25, so it should be 25 square root of 3. So 25 square root of 3, and then 25 cos of 120 is giving us minus 25 out of 2. So this is the vector E in component form. That is method 1. Then we can equally look at method 2 so that we can know the clear difference. So here we have method 2 here, and method 2, we are saying that we are going to consider the angle the vector makes with the x-axis, and that angle here is 30. So it means that our E now, the vector E, that is r cos of theta and r sine of theta, which means our A now is equal to, so r is 25, and you have cos. Now the theta here we know to be 30. That is the angle made with the x-axis, so 30. And then we have here to be 25 sine of 30. Now this is what we are saying. in using method 2, we have to consider the quadrant in which the vector lies. And that one comes into play when we are also looking at the quadrants of the trigonometric ratio. So from trigonometry, we are seeing that the first quadrant, all of the trig ratios are positive. The second quadrant, it is only sine that is positive. The third quadrant, it is only tan that is positive. And the fourth quadrant, it is only cos that is positive. So it means that in the fourth quadrant where the vector lies, sine here is negative. So sine is negative, which means we have to negate sine in method 2. So that's the whole idea. So we come back and we negate sine here. But in the fourth quadrant, our cos here is positive. So it means our alpha is equal to 25 cos 30 is the same thing as 25 square root of 3. And minus 25 sine 30 now becomes minus 25 out of 2. So this becomes the solution of the question. Now we can see that in method 1, automatically you are going to get negative. But in method 2, if you don't apply the idea of the quadrant with the vector lies, you are going to get positive of 25 root 2. And since it's negative, you don't bring it, you are going to get the answer wrong. So these are the two ways that we can solve for the vector in its component form. Now let's try the last but 2 examples and we end today's video. So we have example 3 here, and we want to represent the given vector in its component form. You can equally pause the video and try your hands on this question as well. So we said that in questions like this, then you have to draw a Cartesian plane. So you have it as that. And we are saying that the bearing of the vector is given by the north pole or the positive y-axis to where the vector is. So we are saying this vector happens to fall in the 180 degrees quadrant. So this place is 90. So from here to here is 90. And then it continues to the next one, we have 180. So it means that from the positive y-axis in the clockwise direction to this side gives us 180. So it means that the vector lies on the negative y-axis of the Cartesian plane. So it means that this is where the vector lies. Because when you start from the positive y-axis, 90 and then another 90, that gives us 180. So it means that this side gives us the 180 you are talking about, which means the vector is at that side. Now, this is where the vector lies. So it means that we are going to consider both method 1 and method 2 in solving. The idea is to let us differentiate the two and apply them. So you can apply any of them in your solution. So that is that. Now, for method 1, so let's write it as method 1. So for method 1, we are saying that the vector v, which is equal to r sine of alpha and r cos of alpha. So v is now equal to, now our r was given to us as 7. So you have 7 sine of, now remember that alpha is the original angle given to us, that is 180. So 180 degrees. And now we have 7 cos of 180 degrees. So in component form, the vector v is now giving us, so 7 sine 180 gives us 0, and 7 cos 180 gives us negative of 7. So that is method 1 without considering any quadrant. Now let's move to method 2, where we are going to consider the quadrant in which the vector lies. So method 2, method 2 here, and that formula is giving us v, which is equal to r cos of theta. So cos of theta, I think you have to write it well. So v now is equal to r cos of theta. You have r sine of theta. That is that. So v is equal to, our r is 7 and cos of, now is theta the same thing as 180 degrees? So let's analyze it. Now, theta is not 180 degrees because we said for theta, it is the angle the vector makes with the x-axis. The angle the vector makes with the x-axis. And this vector now happens to fall on the exactly y-axis, happens to fall exactly on the y-axis. So how then do you find the vector, the angle the vector makes with the x-axis? Now this is what you have to see. We are saying that the angle the vector makes with the x-axis. And we can see that this side is the x-axis we are talking about. This is the x-axis. And we can see the vector happens to fall this side. So the angle, the vector in the red pen makes with the x-axis here, that angle is 90 degrees. Because from one quadrant to the other quadrant is 90. From here to here is basically 90. And from here to here also give us 90. From the positive y-axis to where the x-axis is also 90. So the angle the vector makes with the x-axis is basically 90 degrees. So you have that, which means you're going to have your 7 cos 90. And then we have 7 sine of 90 degrees. So this is what I'm talking about. Now we have to consider the quadrant in which the vector lies. So we have first quadrant, second quadrant, third quadrant, fourth quadrant. In the fourth quadrant, we know that sine is negative, which means we negate sine here. So you have negative 7 sine 90. So we proceed by saying that our vector v is now equal to, so 7 cos 90 gives us 0. But negative 7 sine 90 gives us negative 7, which is basically the same thing as method 1. So you can use any of the solutions in your question. So that is that. Now we move to the last set of example for today's video. Stay tuned as we move along. So this happens to be the last example for today's video. And we have here as the vector in magnitude bearing form as 60 kilometers with a bearing of 270. So we write our solution here by first drawing a Cartesian plane. And we can see that this vector happens to form the 270 quadrant. So that is 90, 180, 270. So it means that our vector, now let's see, from the positive y-axis. So from here to here is 90. You continue from here to here gives us 180. From here to here gives us 270, which means from the positive y-axis to this side gives us the 270 angle, which means our vector now lies on the x-axis, the negative x-axis. So this is where our vector is. So we indicate it as such, and we write here as 60 kilometers. That is the magnitude of the vector, knowing what that the whole of this side is the 270 degrees. So we are going to apply method 1 in getting this. So method 1. So in method 1 we are seeing that. Alright, so let's write it nice so that we can all see. So method 1, we are saying that v is equal to, so we have here as r sine of alpha, have r cos of alpha. Well, I think I have to write it also that. So r sine of alpha, and then you have r cos of alpha, which means our v now is equal to, now r sine, so alpha happens to be the original angle given to us, that is 270, and have here as r cos of 270 degrees, which means our v now in component form is, now what is r? We forgot that one. So we know r is r was giving us 60, so it means we have 60 sine of 270, of which we should have included in the second step. So 60 cos of 270. So it means that in component form 60 sine 270 is giving us minus 60, and 60 cos 270 is giving us 0. That is method 1. And when we employ method 2, then we are seeing that, so that is method of 2. my handwriting, so I hope you forgive me on that. So method 2, you are saying that v is equal to, so you have r cos of theta, you have r sine of theta. Now what is theta? Theta here is the angle in which the vector makes with the x-axis. The angle in which the vector makes with the x-axis. Now let's see. The vector itself is on the x-axis. So there is no way this vector can make an angle with the x-axis. The only angle can mix with the x-axis is 0, which means that the angle this vector makes with the x-axis is 0 because the vector itself is lying on the x-axis. So it means theta here is 0 and means that our v is equal to, so you have 60 cos of 0 and you have 60 sine of 0. And you have to consider the quadrant in which this vector lies. And this vector happens to fall in the second quadrant. And the second quadrant, we can see that in the second quadrant, sine is positive and cos is negative. So in this quadrant, sine is what? Positive and cos is negative. So since cos is negative, then means that we'd have to negate cos here. So here we continue, you can see that our vector v is now equal to negative 60 cos 0 gives us negative 60 because cos 0 here is 1 and 60 sine 0 is 0. So it means that in component form, our vector is equal to negative 60, 0. And we end today's video here. Thank you for joining us today. So thank you for watching. Kindly like, you comment, subscribe, and say. Remember that this is BakoMaths, thinking beyond infinity.